Swayam Prabha. Digital India. Educated India.
Hello everyone. So, our present topic is that fiber flow and yarn twist in rotor spinning. So, we will have some simplified assumptions and we will try to calculate the number of fibers at each and every zone and also the yarn twist in normal withdrawal and reverse withdrawal, and normal and reverse withdrawal we have discussed in last session. So, we will try to do some calculation, some numerical we will try to solve based on the fiber flow and yarn twist. So, this is the typical diagram of rotor spinning process as we have already discussed. So, here it is another view here where a sliver is fed from the can, okay, and then a condenser is there, okay, and then it is coming to the feed roller. Okay. Feed roller individualize the fiber by the carding type roller, okay, and it is a sawtooth roller which individualize the fiber. Then feed trough is there is a feed trough through which the fibers are being fed. Then opening roller, it goes to which opens the fiber, the individual fibers are then fed to the transport channel, fiber feed duct, and which transports the fiber to the rotor groove, rotor wall. So, then it goes to rotor. Then from rotor we have discussed that the spun yarn, the yarn is being pulled and take off nozzle is there, the 10 which is called novel or draw off nozzle, and fibers are deposited on the rotor groove, okay, and yarn stop motion is there for in case of any breakage. So, there will be stop, machine will stop, or that particular a winding part will stop, and take up roller and yarn package. So, this is the yarn package. So, this is the simplified process of rotor spinning. Here one thing we should remember, from the sliver to the yarn stage, the yarn goes through, the fibers move through different stages, but everywhere the mass flow rate is maintained, considering there is no waste, no fiber loss. So, mass flow rate means that, and also there is no fiber breakage. If with that assumption we can tell that the number of fibers are flowing per unit time is constant. This is actually that at any point is always constant. So, the operating principle is that the sliver fed usually in draw frame sliver, then sliver opening takes place in the opening roller, fiber is transported to the rotor groove by transport channel, and that is due to the centrifugal force created at the in the rotor and due to vacuum. So, centrifugal force created at the opening roller, okay. Fibers passes from opening roller via feed duct to the rotor wall, fibers collected on the rotor groove it gets collected there. Then yarn formation, and yarn formation process that we have already discussed, that is in yarn group how the twists are being flown to the in the rotor group, and then yarn take off. So, this is the process of rotor spinning. Now, the total draft, if we see, the total actual draft is the text of sliver, this is the text of sliver, okay, sliver text, and divided by text of yarn. So, depending on the sliver linear density and yarn linear density, this draft may vary from 60 to 350. Okay. So, here it may vary little bit more or less, but here one thing we should remember, in rotor spinning the feed material is sliver. And now let us see the draft at each and every stages. In first stages, the first fibers are drafted to the individual fiber stage. So, that is the maximum draft is there. So, this fiber from the sliver are drafted to the individual fiber stage up to the rotor groove. If we see, so it is going. So, it has got 3 different stages. The total draft, maximum draft from this point to rotor groove is termed as V max, sliver to rotor groove. It has got 3 different stages. First major draft is at the opening roller. So, from feed roller to opening roller. So, that is V A, it is a major draft, typically 500 to 2000 at the opening zone by friction between fiber and the tooth of the opening roller. And second is the, it is called pure air draft, V L. So, V A is the opening zone draft, V A is the pure air draft, which is typically 5 to 6, which takes place in the transport channel, transport duct, due to the taper formation and due to the suction created by the vacuum, partial vacuum in the rotor groove. And then the friction draft is at the rotor groove and rotor wall. So, fibers after landing into the rotor wall slides towards the rotor groove. So, during that sliding some draft takes place, that is called friction draft. If we take all 3 together, then that is max, that comes the maximum draft up to the individual stage, it is a V max. So, V max is nothing but V A multiplied by V L multiplied by V F. So, V A multiplied by V L multiplied by V F. So, which is typically around from 5000 to 25,000. So, from sliver to few fibers. So, typically in rotor groove we can have maybe 1 to 5 fibers landing at a time, which is termed as ZS, that we will discuss subsequently. Now, what is back doubling? Next is the back doubling. Back doubling is at the rotor groove, and back doubling is because when number of fibers, that is aggregation is taking place, one by one fibers are landing, and that due to that is a total accumulation of fiber is called back doubling, and which is termed as pi dt by 1000, it is typically 550 to 150. And how to derive this back doubling? Let us see. So, yarn T is the yarn twist, the rotor speed by delivery speed, D is the rotor diameter, and So, 1 by T is equal to delivery speed by rotor RPM. So, delivery speed is equal to rotor RPM by twist per unit length, and back doubling is equal to rotor circumference speed by yarn delivery speed. So, here is the back doubling, then after that the yarn is moving up. So, yarn is actually being pulled at slower speed than the fibers landing. So, if we see here, this is the yarn. Now, fibers are coming from the opening roller through the transport channel at very high speed, but yarn is being pulled at the relatively slower speed. This ratio is the back doubling. So, this yarn, the speed at which the yarn is being joined, so fibers are being joined at the yarn tail is equal to the rotor circumference speed. So, back doubling is nothing but rotor circumference speed divided by delivery speed of yarn. So, rotor circumference speed is pi dn, okay. D is in millimeter. So, to convert it to in meter per minute, this is the pi dn by 1000, and T is the twist per meter. So, T is a twist per meter. So, N by T, N is the rotor RPM. So, just rearranging this equation, we get N cancelled out. So, pi dt by 1000. So, that is the back doubling, and so back doubling is given here. So, draft in rotor spinning, total draft. So, from sliver to yarn, total draft will be that V max up to this point, up to rotor group, and divided by back doubling, that is the total draft given in the rotor spinning. So, number of fibers deposited in the rotor group is typically 1 to 5, that is Z is, okay. Number of fibers per fiber layer deposited in the rotor group will be ZS. So, that is the total number of fibers in the yarn cross section divided by back doubling. That we know that the from the back doubling relationship, we also know that total number of fibers in the yarn cross section divided by back doubling, that makes the number of fibers in the rotor group. So, number of fibers in the yarn cross section is the takes of yarn divided by takes of fiber and divided by back doubling. And now, back doubling is, we know back doubling is pi dt. So, pi dt divided by 1000. So, this is the relationship where number of fibers layer deposited on the rotor group can be calculated by using any of this formula. Okay. Now, try to understand the number of fibers in the cross section at any point of time. The mean number of fibers passing at any given point in the sequence per unit time must be constant. That is the mass flow, constant mass flow, which means at any point of time, at any point. Okay. So, this number of fibers passing will be constant, which means that x f is the number of fibers in the cross section at any point. So, maybe in the within the transport channel, maybe at the exit, maybe on the rotor groove, maybe on the opening roller surface, or maybe sliver or maybe yarn cross section. So, number of fibers, mean number of fibers in the cross section and divided by the speed of fibers at that time. So, if we talk about the yarn, the speed of fiber will be the yarn speed. So, that is always constant. So, this constant if we can calculate, if we can measure, from there we can calculate the speed or number of fibers at any other time point. So, for example, so we have say 3.3 decitex fiber and we are producing 30 tex yarn. Okay. So, this 30 tex yarn is produced from 3.3 decitex fiber, that is 0.33 tex. So, number of fibers in the yarn cross section will be 30 by tex of fiber 0.33, it will become 90. So, we have 90 fibers in the yarn cross section. Okay. So, that is x f is for yarn is 90. So, mean number of fibers passing through the withdrawal point, withdrawal tube. So, that is the withdrawal tube or the mean number of fibers in the yarn cross section multiplied by yarn delivery speed. See, if the yarn delivery speed is given as 50 meter per minute. So, this constant 4500, this constant is valid at any point of that or at any point in the system. So, that is the this constant, this is the constant for the system. The unit of speed is, we can have different unit, but for that one thing we should remember, if we change it so meter per minute to say maybe centimeter per minute, but this constant value will change, but that for that we have to keep maintain the same unit for everywhere. So, at any point of time, okay, number of fibers. So, at any point in the system number of fibers will be 4500 divided by mean speed at that point, and that mean speed will be definitely in meter per minute, not in other unit. Now, try to calculate the number of fibers in the earlier we have calculated from the yarn, this is from the yarn we have got. So, we have got the constant. Now, we want to calculate number of fibers in the on the opening roller surface, except number of fibers on the opening roller surface will be 4500 constant divided by the circumference speed of the opening roller. What is the circumference speed? If the diameter is 60 millimeter and RPM is 9000 RPM, pi 60 into 9000, this is in millimeter per minute divided by 1000. Okay. So, that will come out to be around 1700. So, from there we can calculate the number of fibers at any time, average number of fibers on the opening roller surface is 2.65. 2.65 is the number of fibers on the opening roller surface, and at the feed tube. So, feed at the feed tube exit, so where draft is 1:2 we have given. So, at the feed tube exit the number of fibers will be half of that, 1:2 is there. So, 1.32. So, at this point exit point, so here the number of fibers were 2.65. So, opening roller surface fibers are getting transmitted to the feed tube. and but from the feed tube, within the feed tube there is a pure air draft, that is 1:2. So, feed tube exit is 1.32 and the collecting surface. So, rotor collecting surface, that is rotor groove, where the rotor diameter is 60 millimeter and rotor speed is 40,500 rpm. So, that speed is coming out to be 7,625 meter per minute, the surface speed of the rotor groove. So, it will be typically 0.59. So, 0.59 fibers are there in the cross section. So, what does it mean point? So, we know this is the 2 fibers in the cross section, that is understood. So, 3 fibers in the cross section, okay. 1 fiber in the cross section, this is 1 fiber in the cross section, that is also understood. What is 0.59? That means this value comes because there is a gap between 2 consecutive fibers. So, 0.59 means the fibers are landing one by one after certain interval. Okay. That is why we get the value 0.59. And now back doubling. So, what is back doubling? So, number of fibers in the yarn cross section is 90 and 90 is we have got from 0.59. So, 90 divided by 0.59, I think it is something is wrong there. 90 divided by 0.59, it will be we can see that we can calculate. So, 0.6 is there. So, 90 divided by 0.6. So, we can calculate here. Okay. So, 150 approximately, this is not 1, it will be 155, around 155. So, it is not 15, it will be 155. Okay. So, that is the back doubling. Now, bridging fiber we have understood the bridging fiber. Now, let us see once again the concept of bridging fiber. How does it affect? It causes the normal to reverse withdrawal. So, normal, what is normal withdrawal? This is the normal withdrawal and this is the reverse withdrawal. Here this point is peel off point. From the picture it is clear, from this diagram the rotor rotates in clockwise direction and in normal withdrawal the peel off point also rotates in the clockwise direction. But with the effect of the bridging fibers, sometime this direction of peel off point changes occasionally, but as soon as the effect of bridging fiber goes off, immediately it turns out to be the normal withdrawal. Okay. And in reverse withdrawal, the peeling point, peel off point rotation, the direction of rotation is reverse in the opposite to that of the rotor direction. So, it follows a smooth curve, good appearance of yarn, and here the S formation is there and appearance of the yarn get affected, and it repeats alternately. So, it is not that continuously always there will be normal withdrawal, but the effect of the bridging fiber is not neglected. So, that is why this will be repeated alternately. Now, the probability of bridging fiber is that mean fiber extent divided by circumference of rotor, that is the probability of bridging fiber. Suppose the fiber length is equal to the rotor groove, rotor circumference pi d rotor. If we are using the fiber length of that extent, so that means this is one fiber, this is one fiber which is lying on the rotor groove, and the tail end and leading end of the fiber will coincide. So, there is a 100% probability of the bridging fiber. Okay. So, that means as the fiber length increases with reference to rotor groove, rotor circumference, the bridging fiber probability increases. So, mean fiber extent by rotor circumference. So, that is why in the rotor spinning we cannot use the longer fiber. If we use longer fiber, that means probability of bridging fiber will increase. Now, we can see the effect of bridging fiber here. Initially the twisting is in this fashion. Now, when the twisting torque is created and it is flowing up to the peripheral twist extent, bridging fiber will start wrapping over that, and this wrapping creates the that fiber belts. If the mean fiber extent equal to rotor radius, what will happen? The bridging fiber proportion will be approximately 16%. The wrapper fibers are there. The what is the sum of the fibers, either a loose spiral around the outside of the yarn, but yet firmly anchored on the yarn core. These are the wrapper fibers. The three types of fibers are there: a densely packed core. So, in the rotor structure we have three types of fibers are there. One is densely packed core fibers, then about 80% of the fiber substantially aligned with the yarn. So, these are the about 80% of fibers are there. Then loosely packed fibers twisted around the core. So, first initial layer they will form the core, 80% of the fiber, then loosely packed fiber around the core will be there, and then third one is wrapper fiber, okay, and which contributes to the yarn strength. And due to this wrapper fiber, this is, so what is there in the first core layer, there will be densely packed, okay, and then there will be loosely wrapped on that, loosely packed fibers are there, okay, and over that there will be wrapper fiber. These are the wrapper fiber. So, wrapper fibers, due to the wrapper fiber, the fibers are compressed, and it will actually add to the strength of the yarn. And due to the presence of the wrapper fiber, the main problem is that the yarn, the rotor yarn becomes stiff, and also the untwisting we cannot do. It is very difficult to untwist the rotor yarn, mainly due to the wrapper fiber. Wrapper fiber will restrict the untwisting of the rotor yarn. Now, let us take one example how to calculate the rotor twist. So, 30 takes yarn is there, 4 from the 4 takes sliver. So, 30 takes yarn, 4 takes sliver, 60 millimeter rotor diameter, and rotor speed is 4100 rpm, and its delivery speed is 50 meter per minute. Okay. Now, yarn withdrawal point, that is peel off point, it rotates slightly different speed from the rotor. So, rotor slide peel off point will rotate at little bit different speed, and the main twist is coming due to the rotor revolution plus the peel off rotation. Okay. Due to withdrawal revolution, okay, and or the winding on revolution. So, what is withdrawal revolution? So, due to the withdrawal speed, it will be there will be for one circumference and withdrawal, there will be one rotation of the peel off point, one revolution of the peel off point. So, yarn delivery speed equal to withdrawal rpm divided by rotor circumference, that is the yarn delivery speed. Now, withdrawal rpm will be for this, that rotor withdrawal rpm will be yarn delivery speed. What is that? 50 meter per minute, that means 50 multiplied by 10 to the power 3, that is the withdrawal speed, divided by rotor circumference. Rotor circumference is millimeter, 60 millimeter is diameter, pi 60. So, this will be 266 rpm is the rotor withdrawal speed, NW, withdrawal rpm, that is rpm of the peel off point. So, with normal twist, theoretical normal twist during the normal withdrawal, the twist will be the rotor rpm plus withdrawal rpm divided by the delivery speed. So, 825 twist per minute, twist per meter, and for reverse withdrawal, so when the peel off point rotates in the reverse direction, so effective twisting revolution will be 41,000 minus 266 by delivery speed, it will be 815. That means, the difference between the normal and withdrawal rpm are 825 minus 815, that is 10 rpm will be different, and the effective rpm will be varying from 815 to 825, but this, as this effect is negligible. So, normally in rotor spinning we take the mean of this. So, that is effectively the twist will be rotor rpm divided by delivery speed. So, that is the effective twist. And that is calculated rpm will be for rotor speed by yarn delivery speed 820. In practice, the calculated twist normally quoted, the actual twist in the yarn is 10 to 30% less than the calculated twist. So, calculated twist we can calculate from the rotor speed and yarn delivery speed, which is known, which is in our control, but actual twist in the rotor there will be some slippage 10 to 30% less, but we do not report that. Now, we will try to understand this whatever we have discussed through some practical numerical. Now, try to see here, first numerical is a rotor spinning machine is producing 20 NE rotor yarn from 4 micronear cotton with delivery rate 100 meter per minute. The diameter and speed of the rotor are 40 millimeter and 1 lakh RPM. Okay, that is the diameter 40 millimeter and RPM 1 lakh, and the diameter and speed of the opening roller are 60 millimeter and 8000 RPM. Now, what we have to calculate? We have to calculate the extent of back doubling and number of fibers landed on the transport tube, okay, from the transport tube onto the rotor wall, not in the rotor groove. So, this is the rotor, fibers are transported on landed on the rotor wall, and then it slides to the rotor groove, and this frictional sliding draft at the rotor wall is given 1.5. So, that we have to calculate. Now, let us see. Solution is the yarn count is given 20 NE, that means 29.5 tex. Fiber linear density is 40 micronear. 40 micronear we can convert it to tex with the micronear is microgram per inch, and from there we can convert into tex. 40 micronear means 0.157 tex, okay. And from there we can calculate the number of fibers in the yarn cross section. So, this is the way we can calculate. So, microgram per inch to this much kilometer weighs 4 multiplied by 10 to the power 6. So, from there we can calculate the tex. This tex is being used here. So, we can calculate now the number of fibers in the yarn cross section. So, yarn tex by fiber tex. So, it is typically around 188. 188 fibers are there in the yarn cross section, and if we know the yarn delivery speed. So, what is the yarn delivery speed? It was given 100 meter per minute. So, from there we can calculate the constant K for the system. This constant 18,800, this constant is valid throughout the entire rotor spinning machine. So, this will be used, this constant will be used, we can use at any point of time. So, number of fibers at rotor spinning surface, okay, K. So, that is rotor surface, we can say rotor groove. Number of fibers in the rotor groove will be K 1000 divided by pi 40 is the rotor diameter. So, how are you getting this? I can tell you this one. So, rotor speed, rotor circumference speed pi d rotor into n rotor. So, pi d rotor is the 40 millimeter divided by 1000. Okay. So, circumference S rotor pi multiplied by 1 lakh 100,000. This is the rotor circumference speed in meter per minute, okay, and K is given. So, rotor fiber number of fibers here, okay, and K is equal to number of fibers, this is x f, okay, r. So, that is x f r multiplied by S r equal to K r, which is we have 18,800. Okay. Now, from here we can calculate the number of fiber x f r will be K, that is K by this value, K by, so pi 40 into 100,000 multiplied by 1000. So, this is the value, and if we use K as 18,800, we will get the value of number of fibers in the rotor group as 1.5. So, 1.5 is the number of fibers in the rotor group, and the number of fibers in the yarn cross section is 1.88. So, back doubling also takes place. So, in that we can calculate back doubling here also by number of fibers. So, 188 divided by 1.5 is the back doubling. So, number of fibers in the yarn cross section divided by number of fibers in the rotor groove will be the back doubling. So, back doubling is 125.33, and the second part of the question was that the how many fibers are landed at a time to the rotor wall. So, sliding draft is given, sliding draft was given 1.5, and in the rotor group 1.5 was there. So, if we multiply, so 2.5 fibers are landed at a time on the rotor group, on the rotor wall. It is basically it is a wall. From wall the fibers are slided by 1.5 draft, okay, slided towards the rotor group. Now, next numerical is that a rotor spinning machine is producing yarn from 4 micronear cotton. The 4 micronear cotton is already we have done with a delivery speed of 100 meter per minute. This the data we have already used. The diameter of and the speed of rotor are 40 millimeter and 100,000 respectively, that is also used. The diameter and speed of the opening roller 60 millimeter and 10,000 rpm respectively. The sliver feed speed. So, here the sliver feed speed here, whatever sliver feed speed is 0.75 meter per minute. Okay. Calculate the extent of back doubling and number of fibers landed from the transport tube on the rotor wall. The same parameters we have to calculate, but here the data are given. The consider the friction draft in rotor groove from the wall is 1.5 and the feed sliver linear density is 4 kilotex. So, here the sliver feed is 4 kilotex is given. There is no loss of fiber or damage during it. So, 4 kilotex fiber is given the linear density of sliver, and yarn delivery rate is given, but yarn count is not given. So, we know that we can start from the sliver itself. Now, let us see 4 micronear means we know that 0.157 tex. So, number of fibers in the sliver cross section. So, that we have already calculated this part 0.157 tex. Now, 4 micronear is there, and in the 4 kilotex sliver. So, number of fibers in the sliver cross section will be 25,478. That many fibers are there in the sliver cross section. Okay. So, constant we can calculate from the sliver itself, because we know the speed at that point. So, 25,478 multiplied by 0.75. So, that is 19,108 is the constant. This constant is valid everywhere, even up at the yarn stage, at the opening roller, everywhere it is valid. Now, let us see which is given. So, number of fibers at rotor collecting surface, rotor groove. So, rotor speed is given 10,000 rpm, rotor diameter is given. So, similar way we can calculate. So, number of fibers in the rotor collecting surface is 1.5, and draft will be, what will be the draft, because yarn delivery speed is 100 meter per minute and this feed speed is 0.75 of sliver. So, the total draft is 133.33 okay, here, and number of fibers in the yarn cross section will be number of fibers in the sliver cross section 25,448 divided by the draft. So, it will be number of fibers in the yarn is 191. So, 191 number of fibers in the yarn cross section and number of fibers in the rotor collecting surface is 1.5, that makes the system, the total back doubling will be 191 by 1.5, it will be 127.33, that is the back doubling, and the number of fibers landed at the rotor groove. So, again 1.5 multiplied by the draft there, it is 2.25. Next is a rotor spinning machine is producing 30 tex yarn from 1.5 denier polyester staple fiber with a delivery rate of 100 meter per minute. So, 30 tex yarn from 1.5 denier. So, from there we can calculate the number of fibers in the yarn cross section. The diameter and speed of the rotor 40 and 1 lakh, 40 millimeter and 1 lakh, and the in case of opening roller 60 millimeter and 8000 rpm respectively. Calculate the extent of back doubling and number of fibers landed from rotor from the transport tube to the rotor wall. Same parameter is asked and friction draft is given on the rotor wall. So, similar numerical yarn count is 30 tex and fiber linear density 1.5. So, 0.167 tex. So, number of fibers in the yarn cross section is 180 and constant becomes 100 minus multiplied by 179.6 or 180. So, it will be 179.17960, that is the constant for this system. So, number of fibers in the rotor collecting surface is XF will be XR rotor collection surface pi d, okay, this is the fibers are there, and except this is the constant. Okay. X r is the number of fiber in the rotor collecting surface. So, from there we can calculate the x r as 1.43. So, 1.43 fibers are there in the rotor group, and in the yarn cross section we have calculated 180 fibers. So, back doubling is calculated as 126 approximately, and alternatively we can also calculate that is the number of fibers in the speed of the rotor divided by speed of yarn. So, based on the speed also we can calculate, or based on the number of fibers. So, rotor circumference speed if we can calculate. So, this value pi multiplied by 40 multiplied by 100,000 divided by 1000 is the speed of the surface speed of the rotor divided by speed of the yarn. From there we can calculate the back doubling, which is coming almost same, it is 126, and number of fibers landed on rotor wall will be 1.43, which is the fibers in the rotor groove divided by multiplied by draft 1.5. So, it is coming 2.143. Now, next numerical. In a rotor spinning machine, 10 any cotton yarn is produced from 4 kilotex sliver. Okay. 10 any cotton yarn from 4 kilotex sliver. So, from this data we can calculate the total draft. The machine process parameters are okay, diameter of rotor 40 millimeter, diameter of opening roller 60 millimeter, speed of rotor 100,000 rpm, speed of opening roller 10,000 rpm, and sliver feed speed is 1.5, that is 1.5 meter per minute, and twist contraction is neglected. So, calculate the yarn twist, that is twist per meter in case of normal withdrawal and the reverse withdrawal. Let us try to calculate here. So, 10 NE English count is 59.05 tex. So, total draft here is 40,000. Okay. So, 4,000 divided by 59.5. So, total draft, because 4 kilotex means 4,000 tex. So, sliver tex by yarn tex 69.74, and yarn delivery rate. So, feed rate was 1.5 and multiplied by draft. So, it will be 101.61 meter per minute. So, yarn delivery rate and withdrawal RPM we can actually correlate. Yarn delivery is withdrawal RPM is nothing but yarn delivery rate divided by the circumference speed. So, withdrawal RPM multiplied by rotor circumference. So, withdrawal RPM multiplied by rotor circumference is the yarn delivery speed. From there the yarn delivery rate. Okay. So, withdrawal RPM equal to yarn delivery rate divided by rotor circumference. Okay. And rotor circumference is given, so rotor diameter is given. So, withdrawal RPM is 808.5 RPM. So, this withdrawal RPM, it is called NW, it is expressed as NW. So, for yarn twist for normal withdrawal, so rotor RPM divided plus the withdrawal RPM divided by the delivery speed. So, 992.11, and for reverse withdrawal it will be 996.2. So, the range is from 976 to 992. Next numerical, a rotor spinning machine running at 95% efficiency, producing 20 NE cotton yarn from 4 kilotex sliver with a fiber fineness 4 micron yarn. Calculate the yarn twist per meter in case of normal withdrawal. So, normal withdrawal T normal, okay, rotor RPM plus withdrawal RPM divided by delivery speed. Now, here let us see, we have to calculate the twist, normal twist, T normal we have to calculate. Now, here we need the rotor RPM. So, in this diameter opening roller and speed of opening roller are given, friction draft is given, and extent of back doubling is given 125, sliver speed is given 0.75. The difference in theoretical yarn twist due to normal and reverse is 16 twist per inch. So, that is given, but and no loss of fiber, but to calculate the twist for normal withdrawal we need rotor RPM which is not given, we need withdrawal RPM which is also not given, and rotor diameter is also not given, and also the delivery rate is not. So, we have to calculate each and every component individually, then we can calculate the twist for normal. Okay. Now, let us see this numerical. So, normal T normal is NR plus NW by Vy. So, nothing is given. So, 20 NE yarn, that means 29.5 tex, sliver tex is given 4000 tex, and number of, this is sliver is N sliver, number of fibers in the sliver is 25,499. So, we can calculate, this is sliver tex is given and the fiber tex also we can calculate. So, total draft we can calculate here. Okay. This one is 0.75, okay, and 60 millimeter. So, here total draft is 135.6 and yarn delivery speed is, the back doubling is given here, okay, and between groove and here we can calculate. So, total draft is 135.6. So, yarn tex is given and sliver tex is given, from there we can calculate the total draft. So, 4000 divided by 29.5, it is coming out to be 135.6, and number of fibers in sliver will be, this is coming from the 4000, that means its what is that with the 4 calculated. So, theoretical it is 1.5, back doubling is given. So, producing from 4 kilotex. So, 4000 tex divided by 4 micronear, from there we can calculate the number of fibers in the sliver. So, yarn delivery speed we can calculate, that is 101.7 meter per minute, and withdrawal RPM NW, and so yarn delivery speed we have got. Now, we have to calculate the withdrawal speed and rotor RPM. Now, difference between the normal and reverse withdrawal is 16. So, NR plus NW by VD, that is 101.7 minus NR minus NW by 101.7 is, if we just simplify, we will get 1 by 101.7 multiplied by 2 NW. So, from this equation we can calculate the withdrawal RPM. So, withdrawal RPM becomes 803. So, we have calculated Vy, we have calculated the withdrawal RPM. Okay. Number of fibers in the yarn cross section is 188. So, yarn cross section, yarn text is given, fiber text is given. So, number of fibers in the yarn cross section is 188. Now, the constant we can calculate. So, 188 fibers and 101.7 is the yarn delivery speed. So, 19,109.43 is the constant for this system. Now, number of fibers in the rotor groove is 188 is the fiber in the yarn cross section and 125 is the back doubling. So, number of fibers in the rotor groove is 1.5. So, what we can do? We can get here, this is the withdrawal RPM divided by, that is equal to delivery speed. So, delivery speed multiplied by rotor circumference speed, sorry, withdrawal RPM multiplied by rotor circumference speed, circumference equal to delivery speed. So, from there we can calculate the rotor diameter. Rotor diameter is 39.39, this is will be millimeter, 39.39 millimeter is the rotor diameter, and from there we can calculate, this is the relationship. Constant also valid in the rotor groove. So, in the rotor groove number of fibers is 1.15 and pi dr nr, nr is the rotor RPM. So, that will be the circumference speed of rotor groove multiplied by number of fibers in the rotor groove, that will be constant for the at the rotor groove also. So, from this equation we can calculate the NR, that means rotor RPM, it will be 101,913 approximately. Okay. So, that is the rotor RPM. So, from there what we have got? We have got all these 3 parameters which are required. So, NR, NW and Vy, and by replacing these things we get the rotor twist equal to 1010 approximate 1010.1 twist per meter. So, from the given data we can calculate each and every component by few assumptions. Okay. Now, the next layer is the next numerical is a 46 millimeter rotor running at 84,000 rpm is producing yarn at 120 meter per minute speed. Calculate the yarn twist and number of doubling of fiber layer in the rotor group. So, one is rotor yarn twist and number of doubling. So, rotor twist we can calculate easily. So, rotor diameter is given, RPM is given and speed delivery speed is given. So, rotor twist is rotor RPM divided by delivery speed. So, it will be 700 twist per meter. 700 twist per meter is the rotor speed, and number of back doubling is rotor circumference speed divided by delivery speed. So, what is rotor circumference speed? So, pi rotor diameter multiplied by rotor RPM divided by the delivery speed. Delivery speed is 120 meter per minute. So, 1000 millimeter per minute, because rotor diameter is given in millimeter. So, number of doubling is back doubling is 101. Next one is the yarn of 16 NE spun on 46 millimeter rotor spinning machine at 100 meter per minute speed. Okay. The twist multiplier in yarn is 4.4. The number of fiber layer within the rotor at yarn formation point will be, that means back doubling. So, what will be back doubling? So, yarn count is given 16 NE, rotor diameter is given 46 millimeter. So, delivery speed is 100 meter per minute and Tm is given. So, number of layer we have to calculate. So, twist per meter we have got from the given data 693, that is the twist per meter, and back doubling equal to rotor circumference speed divided by delivery speed. So, rotor circumference speed is pi rotor diameter rotor RPM divided by delivery speed. So, number of layer rotor, the twist is rotor RPM by delivery speed. So, it will become 100. So, number of layers, that is the back doubling, equal to 100. The actual twist in a rotor yarn produced in the with the rotor diameter 40 millimeter and rotor speed is 90,000 rpm and delivery speed is 100 meter per minute. So, it will be very simple. So, rotor speed, rotor diameter will not come into picture, the rotor RPM will be rotor speed by delivery speed, it will be 90,000 by 100. So, 900 twist per meter. The next numerical is a 4.93 kilotex sliver is fed in a rotor spinning machine with opening zone draft being 1400. So, opening zone draft. The draft in the transport duct is 5 and the sliding draft at the rotor wall is 2. If the back doubling is 125, the approximate linear density of output yarn. Now, here draft at every point is given. So, simply we will calculate the total draft. So, total draft will be the draft at opening zone multiplied by transport draft and multiplied by rotor wall draft divided by the back doubling. So, these are given here an approximate linear density of output yarn. So, total draft is opening zone draft, back air draft and the rotor group draft, rotor wall draft divided by back doubling. So, it is 112. So, that is the total draft. Yarn linear density in text equal to sliver text divided by total draft. So, yarn linear density we have to calculate. So, sliver text is given and total draft is calculated. So, it is typically around 44 text. So, sliver text we have it is given 4.93. So, 4930 and the draft total draft we have calculated. So, sliver text is calculated. Next one is that calculate the amount of pure air draft, that is the draft in the transport tube, and the extent of back doubling in the rotor wall. Okay. Producing 20 NE cotton yarn from 4 kilotex cotton sliver. Okay. So, what are the data given? There is no fiber loss or damage, machine production efficiency is 99%, fiber fineness is 4 micronair, diameter and speed of opening roller are 60 mm and 12,000 rpm respectively. Friction draft at the rotor wall and group is 1.5, sliver feed speed is 1 meter per minute, and theoretical yarn twist due to normal and reverse withdrawal are 1010 and 990. This is the theoretical yarn twist. So, what you have to calculate the pure air draft in the transport zone. So, total draft is calculated from the sliver text by yarn text, and delivery speed is calculated because 1 meter per minute is the feed speed. So, delivery speed is multiplied by draft 135.59, and these are given. So, the difference between normal and reverse twist is 20. So, we can calculate 2 Nw by Vy equal to 20. So, Nw we can calculate. So, Vy, that means delivery speed is known, which is 135.59. So, the withdrawal RPM will be 1355.9 RPM, that is a withdrawal RPM Nw, and pi dr. So, withdrawal RPM will be, so pi dr Nw will be the delivery speed. So, from there we can calculate the rotor diameter, and rotor diameter is 0.0318 meter, okay, that is typically 31.8 millimeter, and fiber fineness is 4 micronair, that is 0.157 tex. So, number of fibers in the yarn cross section is 188, okay, and yarn delivery speed we have calculated 135.59. So, the constant here we have got K 25,491. Okay. And we know that normal withdrawal, the twist is 1010, which is given. So, NR RPM of the rotor plus the withdrawal RPM divided by the delivery speed, we know, and from this equation we can calculate the RPM of rotor. So, rotor RPM is 1,35,590 RPM. So, rotor RPM is calculated. So, this is the rotor RPM, and also we know that constant is 25,491, which is nothing but rotor circumference speed multiplied by number of fibers in the rotor group. So, what is the rotor circumference speed? Pi dr nr, all the data are known, dr is known, nr is known. So, we can calculate the xf rotor group. So, xf rotor group, from this 1.88 is the number of fibers in the rotor group. So, and the rotor group and the exit of the this transport tube, that will be 1.5 times, because 1.5 is the draft. So, 1.88 multiplied by 1.5 equal to 2.82 is the at the exit of the transport duct. So, this is the at the exit, at this point, this is the exit point, 2.82 fibers are there. We want to calculate the pure air draft. So, we should know the number of fibers in the entry point. So, number of fibers in the cross section in the entry point is equal to the number of fibers in the opening roller surface. So, number of fibers in the opening roller exit or the inlet of the tube is XTT in, transport tube inlet. So, XTT in equal to pi d for opening roller and n for opening roller, speed for opening roller, which are given, is equal to the constant for the system. From there we can calculate the number of fibers on the rotor opening roller exit or inlet of the tube. So, it is 11.27 fibers are there when the fibers are entering into the rotor group, entering into the transport tube. So, entering is 11.27 and exit is 2.82. So, the draft at the exit pure air draft will be 11.27 divided by 2.82, it will be 3.99. Approximately 4 drafts are there in the during the transport, okay, pure air draft. So, back doubling we can calculate, that is the rotor circumference speed divided by yarn delivery speed, which is 99.9. 99.9 is the back doubling and pure air draft is 3.99. So, we have tried to understand different aspects of rotor spinning, and these calculations will actually from this calculation we are little bit clear about the things, what are the processes going on in the during the rotor spinning. So, we will stop here. We have completed the rotor spinning mechanics. In next session we will start the friction spinning mechanics, and that will be the end of this course. So, our last module remains is the mechanics of friction spinning. Till then, thank you.